Welcome back. I hope you enjoyed your activity this morning and had a great lunch. The lunch you had today was prepared by our food services, so when you come to the university, that you got the first taste of the possible lunches you would have. Before we begin the presentations this afternoon, I would just like to remind you, if you have your cell phone, please put it on the silent, or if you can stay without answering it, turning it off would be also an option. Our first presenter this afternoon is Dr. James Blass. James is the Associate Vice President Partnership and Professor of Civil Engineering, specializing in flood protection, research on sandbag dikes and other new flood fighting products. James was born in western Manitoba and grew up on the family farm near Rivers, Manitoba, where he attended his schools. Today he is going to share some insights into the role engineers play in flood fighting and the role engineering researchers play in helping practicing engineers understand the performance of flood protection measures. Please join me in welcoming James.
Hi, good afternoon, everyone. So the worst slot you can possibly pull in teaching is right after lunch, after that wealth of pizza has been consumed, and I noticed the swarming of everybody, so obviously you had a good morning and were hungry. How was the morning at Fort White? Did everyone enjoy themselves? Yes? Can you respond to me? Did everyone enjoy themselves? Fantastic. Well, we've got a series of great talks for you, at least I hope, notwithstanding mine. They're going to talk about some areas of research and some areas of academic study here at the University of Manitoba to spark, hopefully, your interest in some of the opportunities that you have looking at studying here, of course, in the various faculties of science and engineering. The talk I'm going to give you today is about some of the research work I've been doing for the past 10 years, looking at basically how we can better, or how we can improve the community efforts for flood protection, both in terms of products, materials, and construction. Now, my background is a civil engineer, and so basically this grew out of my interest growing up on the farm, wanting to be able to work with the earth to build things and looking at infrastructure development. And unfortunately, at the time when I came to university, there wasn't a lot of, it was tough life continuing on in cereal crop farming and commercial cattle. And so I decided that I would come to university, get an engineering degree that I thought would help me in the farming side. I never anticipated I would still be here at the university after all these years. I expected I would finish my degree and move on, either go back to the farm or look at professional practice. And so it's been a very exciting kind of series of serendipity that have ended up in me being in this position. And what I want to share with you is that, you know, I've been in your shoes, although it was 20 years ago, and I know it's quite overwhelming to see all the different opportunities that lay ahead, but I hope you look at every opportunity that exists in terms of the different programs in that, and really find what interests you in your heart. And it's obviously important, certainly engineering and science, to have some strength in physics and chemistry and math that you're studying. But really, if you find something that excites you, that's something that's going to motivate you through your university experience. And obviously, there'll be many areas that might excite you. You'll start to hone in on kind of what is best for your skills and abilities and certainly your interests. So today I'm going to talk to you about the science of sandbags, and specifically from an engineering perspective. Now, we've seen a lot of snow, and there's been a lot of reports recently about all the snow in southern Saskatchewan, western Manitoba, and certainly some further south, although not as much in the Red River Basin. When I see a picture like this, I have a very different perception than probably what a lot of people do. People look at this and say, wow, it's a winter wonderland, good skiing, good winter activities. When I see this, though, in terms of the snowpack, I see what is going to turn to water in the spring. And that means this type of activity for me. And this is a picture here of some heavy equipment out building a clay dike, which is considered kind of the gold standard for flood protection when you're looking at building dike structures for protecting homes, communities, and so on. And so what you see here is basically, and I love this photo because of the sign, you see engineers out instructing contractors to build these structures to protect this home and what is a series of homes in a community here in Manitoba. Now, there are a lot of areas where we don't have access or ability to build these types of clay dike structures, so we have to turn to other forms of flood protection, and most notably the one in Manitoba that we certainly are aware of is sandbag dikes. This is a picture from 1997 of a house south of the perimeter where we're seeing here, and for those of you that are familiar with farm equipment will know, is about 10, 12 feet tall. We're looking at a 12-foot sandbag dike structure protecting this home. And we're very unique in Manitoba. This is very unusual to use sandbags to this height. And when we did some study in my research group originally looking at this, what we discovered is sandbags are used for flood protection here in Manitoba, not based on a series of studies and tests and understanding of the mechanics of how these things perform, but based mostly on folklore, passed on through generations of people fighting floods over the centuries. And so as a result here, we can see this sandbag dike in 97, because that was the highest flood protection level we'd seen on the Red River up until that point since the construction of the floodway, was an extremely large sandbag dike. And a lot of the engineers were looking at this and saying, well, wait a second here, is this thing safe? Obviously, we had to evacuate these homes. People couldn't live behind that structure. But there was a lot of uncertainty about whether it was appropriate to use the template for design for sandbag dikes that were typically 3-4 feet high, extrapolate that out to 12 feet in height. So right away, we saw the practice of engineering, an understanding of uncertainty of whether or not this was safe. So the first question is, well, was this really necessary? Or were we just kind of expecting higher water levels than actually showed up? Well, here's the same house when the flood arrived. So you can see here, this is the dike right here. You can see the peaks of the house here. And this photo is the same from a boat. So that dike was completely submerged with a little bit of freeboard protecting it from potential wave action. So right away we saw there was a need to better understand the mechanics of these structures. And this is where the science behind the engineering comes into play. We were very fortunate. We were able to save a lot of homes with sandbag dikes. But of course, that wasn't every single case. We had some successes such as this one. And we had some failures such as this one. And you can imagine the devastation and the emotional impact of having your home flooded to this degree. That's practically the entire main floor of that dwelling. So clearly there was a need to put some better science behind our understanding and look at other methods to protect homes during these types of flood conditions. Now I'm not going to go into the details of all these acronyms, but you can see here this is the standard template that's used. So when people are building a sandbag dike, this is the template that's given to them, and then some information about the height, the width, the top, and so on. But the key thing that I want to share with you is that sandbag dike is basically a series of a whole bunch of blocks that have interfaces upon which they're sitting and have the ability to slip or slide, right? So the key thing is, when we look at how could this sandbag dike fail under hydraulic loading, the first thing we ask ourselves is, where might the slippage occur? Is the weakest between bag to bag? There's the poly sheet that goes up this side. That's the piece of clear poly that you buy that you put into the sandbag dike to stop the water. There's the slippage on the sod itself. A whole bunch of interfaces where sliding can occur that could cause that dike to move and fail. And so right away we can see a research exercise where we have an observation that these dikes are stable up to a certain point, and we have an observation that it's this interface friction that's holding this whole thing together, these different interfaces. So the hypothesis is, if we establish or measure those interface strengths, can we then look at what is the maximum height we can design safely? So this is a graduate student by the name of Tim Cron. We took the materials from those dikes and put them into this big box. It's called a direct shear device. And what it does is you put the different interfaces on top of one another. You apply a load to represent the weight of the dike on top of that. And then you find out what the force is for the frictional resistance along those interfaces and measure them directly to use in mathematical calculations to establish the safety of these structures. So you can see here we put bags right inside the box, put it on top of sod, typical Manitoba, and then we shear it back and forth to get those strengths. And of course, a lot of you will be exposed in your mathematics right now in your science classes to Cartesian plots. You can see this is data. This just shows strength versus the height of the dike. These points here measured by that device are the first evidence to recognize quantitatively what the interface resistance is of all those different interfaces inside the dike. I'm not going to go into details, but you can get a sense from the physics and math that using that information, we can now create mathematical models that allow us to calculate what would the failure surface look like in a dike if we reached the maximum load. From a scientific standpoint now, we've got a lot of physics in this, we've got a lot of mathematics, but we're engineers. And in engineering, we're not going to believe simply the calculations, what we do in the lab. If we want to really believe something, we're going to go build it and break it. And that way we know that we've actually reached catastrophic failure. So what we did then is we went out and built 8-foot dikes. We built them with all these instrumentation inside here. The instruments are devices that tell us how much the dike is moving, how much water pressure it's feeling at different places inside, and how much stress it's feeling. So as the dike starts to shift under the water loading, we can sense that with these sensors. We went out to the field, built that structure, so we could build an isolated segment of dike right in the field. And all those instruments that we put in there, you can see are all wired up here, all coming up, and they're going inside that dike. And what that does is allows us to then load this dike up with water in behind, and we can measure what that dike is feeling as that test is progressing to validate what our mathematics and physics have told us is in fact correct. I'm going to show you a little video, and I think we've got the sound off because this was taken by a few of my graduate students, and there's a little bit of unfavorable language at one point because they got rather excited when the thing failed. But what you can see here is this is the dike. We've got a little bit of movement the video is focusing on at a couple of points, but basically it'll shift over to the center, which is what I want to focus on. And so what you're going to see now with this video is we're getting significant amounts of seepage. You'll see the water level back here is getting very close to peak level. This is an 8-foot structure. You can see here, these are the leads for the instruments coming out, and what we're seeing is a lot of dirty water inside here. What we're measuring is actually as that water is flowing through the dike, because these bags are just weaved polymer materials, they're actually porous, and the sand inside is porous as well, so we're getting water flowing through that's dirty, which is basically the loss of the clay fraction, or the very small particles are actually mobilizing and flowing out of the bags themselves. But the key thing we're focusing on here is the water coming out. We're seeing small movements. They're hard to pick up from the camera, but you can see more water coming out starting, and eventually here, we're going to start to focus in on this area, and you'll see some movements as we're leading to failure. Of course, only in Manitoba do you get a mosquito landing on your lens during your testing. So here we go. We're moving. He's actually covering up what's happening on the one side. That there is the first slippage. We're seeing bag-to-bag slippage. We're seeing more water now, which is lubricating the interface the failure is happening on. All these instruments are telling us the water level pressure is rising, 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 rising inside, and we're seeing now the whole thing leading to catastrophic failure. This end gives way, and then the entire structure starts to collapse. And so for the first time, we have measured evidence of the collapse of a sandbag structure with all the instrumentation telling us exactly what it's feeling and how the water pressure is driving that failure. That was pretty exciting. The results of that validated what the physics and math were telling us, and we've now been able to introduce that into policy and planning so that there are now limitations. The dikes can only be built to 5 feet high using the standard template, after which a professional engineer is required on site to validate some changes to the geometry to ensure stability over the 5-foot height. And so we're seeing research now directly making its way into engineering practice and obviously into an area of considerable importance to protecting communities and citizens in Manitoba. My research group now is doing a lot of work looking forward to new materials and new products, better ways of building flood protection structures. And we're looking here, these are some Hesco structures. Anyone was involved in throwing sandbags in the flood in 2011 in western Manitoba along the Souris, or anybody? There, we got a couple of people. You might have seen some of these Hesco barriers. They were deployed in a few places, including along the number 1 highway near the Sandhills there. What's the park? Camp Hughes. And so we're seeing some of these new materials now being brought out, and so we're doing a lot of testing on those to validate their benefits over the sandbag dikes. Similarly, we've got these tube products, another type of product. But the point being, we're looking at all sorts of new options that can be used for flood protection, because the sandbag dikes have a lot of limitations. And although they've been used for some time and they still provide tremendous value and people trust them, there's a lot of opportunity for new types of products that can be deployed much more rapidly, require less resources, can be done, obviously, like I said, more quickly, and they provide a lot more benefit in terms of rolling out in certainly urban areas flood protection very quickly. So I hope that gives you a sense of kind of what, this is just one area of engineering, but the point being that we apply the scientific method in all of our work to understand how the science behind materials and infrastructure is absolutely critical to understanding the limitations that those materials and infrastructure can withstand. And then we look at testing that in an environment where we can actually push it to its limits, and then as a result understand behavior. Thank you very much. Sure. So we've got time for a couple of questions if there are any. I'll field any questions about engineering too. I'm happy to promote it over all the other areas. No questions? Sorry, go ahead. Yes.
I just had a question about your model versus the river, like the turbidity or the flow. How is that worked into it? Because that was a static model, wasn't it?
This was a static test, and generally we work with one variable at a time, and so static water was the first one. We have a wave facility also. out in Smart Park that we do wave testing as well. But generally, sandbag dikes are constructed in areas beyond the riverbank where there's tree frontage to avoid exactly the dynamic water effects, because that has a big impact on performance. And moving water, debris, wave action, even from passing watercraft, can have a very, very bad effect on sandbag dikes. So your point is absolutely critical. But yes, we've been looking at that. Sorry, yes, go ahead. This is civil engineering. Anything where you're dealing with the infrastructure, you're dealing with building things, materials, is generally civil engineering. I think the distinction the mechanical engineers like to use is mechanical engineers build weapons, civil engineers build targets. Right? So, yes. What might your forecast be for That's the area of civil engineering that deals with forecasting is called watershed processes and systems. And their sense is certainly on the surface, there are some concerns. The snowpack in southern Saskatchewan that of course flows down into Minot and back up is high. I think it's almost 2 times normal conditions. But I'll be honest with you, I don't know, because the watershed processes, people tell us how much water is coming, and my specialty is to stop it from getting into your homes. Any other general questions? No? Thank you very much.